All right, so we had introduced magnetism, and I think the last thing we did was to discuss the magnetic force. And we went through several exercises in class with the right-hand rule. So any questions about that? Continue on with discussion of magnetism and look at several applications, I guess you would say, of magnetism associated with moving charges. So as I mentioned to you in that discussion, we have, magnetic, we talked about magnetism is created by a, moving charge, translating, rotating, vibrating. But when we were looking at the force, we weren't really discussing, we were assuming that the force associated with that moving charge was negligible as compared to the external force that causes, the external field that caused the force on the charge. So we're still in that mode. And we said that the force one of the characteristics that the magnetic force is at right angles to both the velocity of the moving charge and the external magnetic field causing the force. Yeah. We then use that to define the magnitude of the field. We said it's equal to the magnitude of force divided by QV sine theta. We've got the units. Let's consider an application of the magnetic force with mechanics and Newton's second law. Let's say that we have a magnetic field in a region, and I don't know, I'll put it out of the board, let's say. So remember that notation. It's a constant field, so the space between the field lines is the same. So this is B external. And I can switch on this field whenever I want. I can turn it on and off. I have a switch. Let's assume that we have a moving particle that is translating from left to right from your vantage point, and I turn on this field whenever I turn on this magnetic field whenever the charge is right in the vicinity of the, right in the midst of the field, or of the region of space that defines the where the volume of the field exists. And so let's say that the direction of the velocity, as I said, is to the right. So that's a velocity vector that defines the velocity of that particle at this particular point. And let's say that the particle is a negative charge, and that negative charge is right here. So at that instant time, we've got this negative charge that was moving prior to turning on the field. So let's say that the charge was moving first, and then when it's at this point, I turn on the field, and the field is in the orientation that I have described. And if I had not turned on the field, the charge would continue to move along the line that I have described here. But we do know that the that the magnetic field is on, and so it's going to apply a magnetic force. And yeah. So I want someone to tell me what the direction of that magnetic force will be on this charge. In fact, I'm going to call on Mushkan. Can you tell me what is the direction of the magnetic force on this moving charge at this instant when I turn on the field?
Is it 1 second?
Yep. Take your time.
Wouldn't it be going up?
Yes. Can you walk the class through the process? Run
So
wrap point. Yeah.
I would point my hand facing back, and then I would curl my fingers to the right, making my thumb face up.
Do you mind? Can I watch you? Kind of hard for me to follow.
I mean, I just woke up, so I look great.
Okay. All right. So, well, that seems a little. I mean, you got. I do believe it's up, but I couldn't really follow that very well. Could you explain one more time, please?
So I took my arm and I face it going back because
When you say going back, can you? So back, that means into the board or
out of the board.
out of the board.
And
I
then,
don't know. I don't know if I'd agree with that. Right.
well, doesn't the red dots represent that it's coming out of the board instead of into the board?
The red dots do represent the magnetic field coming out of the board, but be careful with this cross product. It's Q, which is just, it's out of the biggest constant multiple, but it's V cross V, not V cross V. Right? Remember with the cross product, it's the first vector crossed into the second vector. So in the run wrap point, you run your fingers in the direction of A, right? Cross them or wrap them toward B, if I'm doing this right here, toward the second vector. And then your thumb points in the direction of the resultant vector C, and then you have to flip it. So point, yeah. And then you flip if it's a negative sign. So you started off by, I think, saying this. Well, that's, yeah. So you probably would get the right answer if you didn't flip, because it's throwing in a negative sign. So if you did B cross V, B cross V, yeah. So basically, by doing that, by flipping those vectors, you put in a negative sign, so you didn't have to do the last part. But that's not really the way we do the cross product. So what you did was B cross V. Do you see that?
Yeah.
Yeah. So what you want to be careful about that. It's V cross B. It's the velocity first, right? So run, and then now I'm going to have to orient my hand so that I can wrap my fingers so that they're pointing out, and point, so that's down. But because it's a negative sign, I have to flip. So that's what I would suggest. But you got the right answer. In this particular case, it was I guess when you flip it around, basically that's kind of like it's like using your left hand or something like that. Put in an inherent negative sign. But let's be careful about that. But good. Yeah. All right. So stay with me here. So initially, the force on this particle is up, straight up like this, right? But the particle has momentum, so it doesn't stop moving. Now, if it were stationary, it would just accelerate up. But right now, it's got acceleration up at that point, but it still has momentum in the horizontal direction. So it continues to move. What would the motion look like in the next instant? What would the path look like, in the next instant as it begins to move? When you now combine, now remember, if there were no field, it would move along in a horizontal direction at constant speed. If there were no velocity and it was just stationary, it would accelerate up at a constant speed. It would accelerate up at a constant acceleration. speed increasing in that direction. But what we really have here is a combination of two different motions, constant motion to the right and accelerated motion up. So when you combine that motion, what would the path look like over the next, couple instants? Armando. What would the path look like? Are you there, Armando? Okay, Edmund. Hello? Hello, Edmund? Not sure? Okay, David Edwards, you want to give it a shot? You had me for mechanics, so I'm counting on you. What is the combination of accelerated motion in the horizontal direction and, constant motion in the horizontal direction and vertical motion, and accelerated motion in the vertical direction? You combine those, what type of path would you get? David, you there? You know what, Mushkan, why don't you go for it?
Okay. What did it go?
Oh, hold on. David, Nuba. David, where's David? No, Dami. I'm sorry, I can't see. Yeah, Dami. It would be, well, you're right. That language that I use, it would be parabolic if the force were constant. But you're on the right path. Mushkan, why don't you go ahead and, since I called on you, why don't you go ahead and follow up? It's not, I wouldn't quite say parabolic, but not necessarily. But go ahead, Mushkan, what are you going to say?
I thought maybe it would move diagonally, maybe like in
Like this?
Yeah.
Okay. Okay. That's on the right track. Yeah. Definitely it's going to change direction, but it's going to do that. So what happens is the reason it's not diagonal, but really the answer I'm looking for is that it's a curved path, not necessarily parabolic, Dami, but curved. So let's take a look. So let's say that, I mean, if it were a diagonal, that would mean that at some point it would have to change direction abruptly, you know what I mean? Maybe you have to just develop a sensibility for that. But it doesn't change direction abruptly. It changes direction gradually as you take the limit as delta t goes to 0 as soon as you turn on the field. So it's going to be something like, it'd be something like that, right? And let's say that I'm making it large because you have to see it, but that would happen in a very small delta t and over a very small delta x arc length. But the reason that it would happen gradually is that in order for it to stay in a diagonal path, it would have to be basically moving at a constant speed, right? So somehow, if I turned the field on and turned it off, then yeah, it would change it abruptly, but then it would move along a tangent to that line, but the field would be off. Do you see that? You see why it wouldn't be diagonal?
Yes.
So if I but if I kept the field on, so let's say that it's at this point now. What is and since you did it initially, why don't you go ahead again, Mushkan? Now that it's at this point over here, what is the direction of the field when the charge is at this point? Sorry, what is the direction of the force when the charge is now curved a little bit and at that point?
Well, wouldn't it still be? Oh, what it would move? It would be. I don't know. It would be. So it would be. Is the is V still moving to the right?
Remember,
Still put
no, remember V is always going to be tangent to the path. So if at that point is when the charge is and it kind of curved around like that, at that instant, the velocity vector is pointing tangent to that path, which is something like this. It's always going to be tangent to the path at every point V is. So now V is like this. And B is still straight out. So if V is like that and B, and remember, F has got to be perpendicular to both B and V, the result. So what would you get right there?
Wouldn't it face the top left? Wouldn't it be going in that direction?
Top left. So like in terms of like, I don't know, let's say north is up and down is south, right is east and west. So can you?
Northwest.
Yeah, it's going to be like in that direction somewhere, like northwest. That's right. So let's walk through the class. So run wrap point. So run your fingers in the direction of the velocity, right? So your arm always has to be parallel to the velocity, but the velocity, remember, is always tangent to the path. So it's curved, so it's like that. Still have to wrap my fingers out, orient my hands so that I can make my fingers parallel to B, which is out of the board. Then point, which is basically southeast, but then it's negative, so I have to flip. So that's northwest, something like that. So if I draw it in, now FB is perpendicular to both B and B still satisfying that final result, and it points like this, okay? Now, the thing is still moving though. It still has momentum in, I guess, what you would say the northeast direction. So it continues to curve around, right? So let's say now it curves again so that it's maybe something like this. So that if I were to compare it to the original velocity, it's moved about 90 degrees compared to where it was initially. The velocity, that is, the direction of the velocity. If it's right there, I draw a tangent. That tangent line is going to be basically straight up now. And in that orientation, we'll go to someone else. Ashura, what would be the direction of the force on the object when it is now at, when it is now moving straight up? So we've done three positions. We've done position 1 here, position 2 here. Now we're at position 3. Where would be the direction of the force on the particle at position 3 when its velocity is straight up? Shura.
I'm not entirely sure, but can you walk me through it?
Yes. But you start. Run wrap point is what we're doing. You got to learn this. So start with run. How would you orient your hand in that way?
So because the velocity is going up, my thumb will be going up.
Ouch.
And then the third position being that 3, my index finger will be facing towards the board.
Back up.
Sure.
Did you say that your thumb is going to be pointing up?
Yes.
So you're using this method here, this thing?
Yes.
Okay, let me teach you that method. You're backwards. With that method, it's the index finger that starts.
Index fingers, my bad.
And then your middle finger, and then your thumb is the final direction of the force. So go for it.
All right, so index finger facing up. The position of 3 would be going diagonal. So would my thumb be facing downward? So
You lost me. You're pointing your index finger in the direction of the velocity. That's up. What was the second? What was the second process? What did you say?
Wouldn't my middle finger be going towards the right of the board?
Why?
The position 3, oh, sorry. So after position 3, it's going straight up, correct? Because I'm looking at the other line right next to it where like the 3 is on top of, as opposed to where the dot is as for the second.
Position, no, that was for the problem we just did. Position 3 is this dot right here. So this is position 1, position 2. That line right there is associated with the velocity for position 2. This is position 3, and the line straight up is the velocity associated with position 3. Hello?
Yes, I'm still here.
So let me ask you something, Shora. Can you just tell me what run wrap point refers to? Can you just walk me through that process and tell me what it is that means and what you're referring to?
If I were to, gosh, I'm not sure how to like actually kind of put into words.
I wrote it down. Did you write it down in your notes when I first gave it to you? Can you look back there and just read off what the process is?
Was this last Monday or?
I'm not sure when it was. Let's just do it right now. Process is run wrap point. Well, even you're doing the 3-finger thing. It's the same thing. I've just kind of done it in my own words. When you're using the 3-finger, what can you describe what that is? What are you doing? The first finger does what? The middle finger does what? The third finger does what?
So first finger does velocity. Typically, the second finger
So
does.
stop. I said does because I want you to explain it. Like does is not an explanation. What
Okay.
does it do? What are you doing with the first finger?
Okay, so the fingers are facing the orientation of the vectors for the corresponding motions.
Wonderful. Go for it. Keep going.
So with that being said, given that we have velocity, typically the index finger follows around that path, and then the other two motions based off how our fingers are, because there's no indication of negative, it's going to be no flip. So the sorry, what's the FB step for again?
So let me help you, Shora. You're not. It's not specific enough. Okay, FB is a magnetic force. So you gotta be a little bit more specific about that. And it's just simple. You're overthinking all of this. The first finger points in the direction of the velocity of the particle. The second finger, the middle finger, points in the direction of the field. Thumb will then point in the direction of the force associated with that particle and the force on that particle. Does that make sense?
Yes.
That's it. And in the case of a negative charge, you still would have to flip. Again, if the charge is negative, whatever that final direction of your thumb is, you'd have to flip it 180 degrees. So that's what you're doing. Your index finger points in the direction of the velocity of the particle. The middle finger will then point in the direction of the field, the external field that particle is moving within. So you'd have to orient your hand so that your middle finger is doing that. And when you have those orientations aligned, your index finger in the direction of the velocity, your middle finger in the direction of the external field, then your thumb points in the direction of the force that external field is applying to that particle. If it's a positive charge.
But
if it's a negative, go ahead.
Sorry, so because it's negative, would my thumb be facing towards the board?
You give me the final answer for this one?
Yes.
Why don't you back up and walk me through every step?
All right. So my velocity is facing up. The magnetic field is towards the left, so my middle finger is pointing left.
How do you
And
get the magnetic field point towards the left?
is it the FB like in the like the FB like on the board is like towards like the second quadrant of that line or so, or
So sure, we've done this. This is the third time we're doing this. This number one, this is the magnetic force when the charge is at position 1. Position 2 is here. This green line is the magnetic force that we determined for the charge at position 2. We are at position 3, and we do not know the direction of the magnetic force, FB. That's what you're trying to find out. So there's no magnetic force there. 1. 2, the cross product is between V and B. V and B. You understand? The
yeah.
velocity of the particle and the external field. Now, I talked a little bit about confusing force and field. Let's continue that discussion. There is a magnetic force and there is a magnetic field. The magnetic field is magnetism, the thing that makes it's like well, it's just, I don't know what else to say. It's, you know, I looked at defined it before. It's like, you know, there's a difference between an electric field and an electric force. Magnetic field is akin to that. So there's a magnetic field in the region, which is represented by these red circles with dots in the middle of it. And it permeates the whole area in which this velocity, this charge is moving. You wouldn't be able to see the field. Just like I can't see a gravitational field, but it's in the space of this room right now. And if I were to put an object in that room and drop it, I would have evidence that there is a magnetic field there, because that magnetic field would apply a force to that object and make it accelerate down. There's a similar analogy between a magnetic field and a magnetic force. The magnetic field is permeating the area of this space and it's pointing out. And now if I can, there's evidence that there is a field there, I can prove or determine that there is a field in that area, region of space, because if I allow a charged particle to move, then that charged particle, the motion of that charged particle will be diverted because that field is there. So I guess that's I don't know, that's what I can explain it. But up here in the cross product, you're crossing V into the magnetic field. So can you tell me again, where's the direction of the magnetic field in this region of space where this charge is moving? Sure.
Well, since we can't see it and it's like affecting, wouldn't it be the opposite direction of velocity?
Well, in general, you can't see it, but I've told you what direction it is. I've written it right here on the board.
So the B external force is moving towards the right.
I don't understand. Like, I just don't understand. Why are you saying it's moving to the right?
Sorry.
Like, why? Where are you getting that from? You see that, you see these dots here, right? Do you know what
Yes.
that means? What does that mean? When it's a circle and a dot, what does that mean? Do you remember?
No.
Okay. Yeah, and you know, it may be a little bit uncomfortable thinking on the spot here. I know that's difficult. So just, I'm with you, but I'm also trying to give a little tough love here. So now this is when you have a vector notation. We did that before. Vector notation, when you have a circle and a dot, that means that the vector is pointing out. When you have a circle and a cross, that means the vector is pointing in. You remember we said that several times over the course of the semester?
Yes. Sure? Yes, I do.
Okay. Yeah, so that's what we're that's what the notation I'm using here. Okay,
Okay.
so the magnetic field is out of the board, and the velocity vector at this instant is going straight up. So that you have your two directions, you have velocity and you have the external field.
Okay,
try-
so
Go ahead. Go ahead.
velocity pointing up, middle finger, and force is pointing towards me. So that leaves my thumb pointing towards the right, but then since it's negative, I'll have to flip it. So it will be, so velocity will be pointing down. The vector field will still be affecting me towards me. So my thumb will be facing the left side of the board.
So that's your answer. The magnetic force is pointing to the.
Yes.
What's the answer?
That my thumb will be facing towards the left.
I agree. The magnetic force is pointing toward the left. And yes, to use Shore's method of preferred method, the finger method, index finger pointing in the direction of the velocity. The middle finger, still you have to orient your hand so that the middle finger is pointing out toward the direction of the magnetic field. My thumb then points to the right, but because it's negative, I have to flip. So in this case, the magnetic field is going to be pointing to the right. So let's recap. What has happened is this charge is moving along, minding its own business. I turned on the field. At this instant, it felt a force. It started to curve. Continue curving. At that instant, force is pointing in. Now force is pointing like that. So in the next instant, it's going to continue to curve. All right. So let's say that, we kind of move this along. So let's say that it curves and it continues curves and like it curves up another 90 degrees, like it's at the top up there. When it's up there, what is the direction of the field? Can anyone see the pattern that's developing? That's someone who hasn't done. David Wabo. I don't know if you. When that particle is moving there right now, what would be the direction of the force? It's called this position 4. What is the direction of the magnetic force on the particle when it's at position 4? David Wabo, are you there? Angel, talk to me. Angel Contreras. Yeah, it's so frustrating. Yeah. Yeah. Can you repeat the question? Yeah, folks, it's really frustrating. I mean, I know I'm not picking on you, Angel, but like, if you're going to be in class, like it wastes time when I'm calling and people, I guess you walk away and stuff like that. And I haven't really been on you about putting your cameras on for obvious reasons, once you feel comfortable, but you got to look at it from my point of view. Like, this is really frustrating when if you're in class, then it's just like we're in real time. Like, if you're not going to be in class, you're going to walk away, you're going to do something, then don't be in class. Yes, Dami, it's down, right? Can you walk the class through that process?
So if you use the run by point method, the direction of the velocity will be pointing towards the left. Then
Yes.
the direction of the magnetic field will be pointing out of the board. Then once you point your thumb out, the direction of the magnetic force will be pointing upward. But then because it's negative, it'll flip and point downward.
Very good. Wonderful. So run, wrap, point, flip, down. So yeah, Angel, that was the question. What is the direction of the magnetic force on the particle at that point? That's right. So what is the pattern that's developing? Monica, are you there? Can you answer that? Can you see what's happening? For example, so it's going to get a little bit messy here, but let me erase that. So it's pointing down. So if I keep going, right? If I keep going, like let's say it curves another 90 degrees. So curves on around, it's over here. So like Monica, what is going to be the direction? What pattern does it look like this thing is mapping out? Monica.
Circle?
A circle, that's right, that's right. And the magnetic force is pointing toward the center of the circle at every point. What does that remind you of from mechanics? What type of motion?
I kind of remember the name, but I don't.
Okay, that's fine, that's fine. Let me help you a little bit. So it's motion where we have, like, look what's happening here. And now, let me ask you this, Monica. Is the velocity, so, well, yeah. Just let me answer this way. So we said that there was initial velocity v. Now, you know there's a difference between velocity and speed. The speed of the particle is also v, but it has a specific direction, you know, like, I don't know what that would be, to the right. So let's say that the speed of the particle is v. When I cut on the field, does the speed of the particle change at all as it moves around this curve?
No.
No, it doesn't. Does the velocity change?
Yes.
Yeah, because it has direction. It's not rotational, Dami, but good. It is rotational motion, yes, but it's a special class of rotational motion, is the word I'm looking for. And it's a situation where an object will move in a circular path, as Monica said, with a constant speed, because as she just said, the speed doesn't actually change. So it was motion in which the speed, it was circular motion in which the speed is constant. Jason, you want to help me out? Remember that what I'm looking, the terminology I'm looking for?
That's the best I can think of is circular motion with constant velocity, or yeah, but I can't think of anything more specific than that.
Okay, fair enough, fair enough. Let's see, finally, who I haven't called on today? Lucy, I haven't called on you today. And AJ, any of you want to contribute or chime in? You remember?
Yeah, I agree with Jason. Like I was gonna say circular motion, but I don't know what else to say to that.
Okay, it is circular. We called it uniform circular motion. That's true, but it also has a kind of a pet name that most people refer to when you. Yeah, so uniform circular motion. Does that jog a memory? Well, uniform circular motion had a specific type of force and a specific type of acceleration associated with it.
Okay, right.
Yeah, Lucy, are you there? You're...
No, I don't remember any specific name. I just remember circular motion.
Okay, all right. Go ahead. Yeah, it's okay. Oh, who is it? Dami, there you go. Dami, yeah, you gotta go ahead and you wrote it. Go ahead and say it to the class, Dami. I think you got a microphone.
Centripetal.
Yeah, that's what I'm looking for. Centripetal motion. Better remember that. Centripetal motion. Centripetal acceleration, centripetal force, centripetal. And yeah, you can refer to it in the way that Jason and AJ did. It's a uniform circular motion. Uniform circular motion has a centripetal acceleration associated with it. Does anyone remember any characteristics of centripetal acceleration? There are a couple that are. Go ahead, AJ. Yeah, it seeks the center. The acceleration is always toward the center of the circle. And what's the magnitude? You probably got that from high school. The magnitude of centripetal acceleration is You remember, AJ?
A tangent?
It's the mag. I'm looking for the formula, basically. Is what I'm asking. You remember?
Yeah, I forgot. It was like,
That's okay. Let me help you. AC is defined as B squared over R. You probably remember now. You probably remember that, right?
yeah,
B
and then,
squared.
okay. Okay.
Yeah. So that's that's centripetal acceleration is and it always points toward the center of the circle. That's a characteristic, right? Of the motion. Points toward the center of the circle. Now, what we have here is force, not acceleration. So what's the connection there? Because we know that if something is accelerating, it's got to have a force, right? That's so.
Newton's second law.
Yeah, wonderful. Newton's second law. So, ouch. So yeah, Newton's second law says that the net force on a particle equals the mass of the particle times the acceleration. Now, I know most of you didn't have me for mechanics, but what I teach with the second law is you always have to evaluate the motion first. Think of it, let's have a quick review. With Newton's second law, I like to think of it as two separate sides. There's a kinematic side, the motion side, and there's the dynamic side, the force side. Before you even use Newton's second law, you've got to know that something is accelerating, right? You have to, and how do you know that? You just look at it, you observe it. If you see a car moving along the ground, horizontal, is it moving at a constant speed or is it moving at an accelerated speed? You just intuitively can see that. If it's moving at a constant speed, you don't even use Newton's second law. You have to go to Newton's first law, net force equals 0. If it's accelerating, like for free fall, when I drop this object, I can clearly see that the thing is speeding up. So I know that it's accelerating. So therefore, I know I must apply Newton's second law. So the point is that you always have to evaluate the motion of a system first before you can know which of Newton's laws to apply, the second law or the first law. That's something that I really drill in. So those of you like David Edwards and a couple other people who had me, so this should be pretty review to you. But for those of you who haven't, that's one thing that we want to remember, that when it comes to mechanics and motion, you have to evaluate the motion first. And there's a couple ways you can separate motion, linear, rotational. But the first thing, before you even get into the kind of motion in terms of linear versus rotational, there's a much more fundamental thing that you have to assess. That is whether it's accelerated motion or constant motion, because whether it's linear or rotational or oscillatory, whatever, it's still going to either be constant or accelerated. So that's the first thing that I would assess. So in this case, we have to see in this motion, we have actually determined that even if the speed is constant, it's accelerating. And we could, even if we didn't remember centripetal force or any of that kind of motion, as Monica pointed out, if you understand the definition between a vector and a scalar, you can see that that's happening. That the velocity is changing because its direction is always changing, even though its magnitude is not. Right? And we also see by evaluating it that the force is toward the center of the circle. And that makes sense, because if now you do remember that there is uniform circular motion associated with this, then now you can say a little bit more about Newton's second law, because if you evaluate the motion and you see that it is a centripetal acceleration, which is a characteristic of this kind of motion, then that means, I can put a little subscript here, the acceleration is centripetal, but that means the net force is also a centripetal force. Now, that's the other thing that I want to say as a review for centripetal force. It's something that can confuse people. Whenever you evaluate the motion of an object, and it is experiencing a centripetal acceleration, there is no individual force within this net force that is the centripetal acceleration. It will always be the net force on the object that is the centripetal acceleration. Now, if there is only one force, like in this case, well, in this case, the magnetic force is acting like a centripetal force because there are no other forces on it. But one of the confusing things about centripetal force when people are first learning is that, say, for a Ferris wheel, for example, like if I'm sitting on a Ferris wheel and I'm going around at a constant speed, well, at every point, there's more than one force on me. There is gravity, which is always pointing down, but there's also the normal force because I'm on the seat. Neither one of those forces is a centripetal force. It is always the combination of the forces on the object that is a centripetal force. So at every point, I have the gravity pointing, well, gravity is always down. The normal force is going to always be pointing up. It's going to be changing its, but what's happening is the value of the normal force is changing. Just like if you're on an elevator, right? When you're going up, you're heavier. When you're going down, you're lighter. The same thing is happening in the vertical direction for the normal force on the Ferris wheel. But you know, generally speaking, generally people evaluate that particular problem, the Ferris wheel problem, at specific points, like at the top or the bottom, and they can use it to determine various things, like, you know, whatever they ask you. But my point is that it's always going to be the net force that is the centripetal force. So you have to first look at all forces on the object, all the different forces on the object, look at the motion and evaluate it to understand that it's centripetal, and then you will understand that the net force, and add those forces up according to their relative directions, and that entire net force will be the centripetal force. Now, in this particular case, we only have one force on the object, assuming I'm negating gravity. We're assuming it's in a region where these forces are much stronger. So let's put that caveat in. That is this example, I'm assuming it's an ideal situation where I'm assuming that, sorry, it's an isolated system where we're not considering gravitational force. And I would have to specify that because we could be, but so, you know, assuming negligible gravity, negligible weight. So, assuming no gravity, then we could make an equation from Newton's, we could apply Newton's second law to this problem. We could say that the net force, which is the magnetic field FB, is equal to the mass times the centripetal acceleration, equation 1, 2, 3. But now I could, in fact, I want you to do this. Let's say that we know, like, let's give this particle a specific, let's quantify this a little bit. Let's say that this particle is a proton. No. Actually, sure, why not? Let's say that this particle is a proton. So these are all values you should know. Let's say this particle is a proton. So assume a proton enters a region in which the magnetic field strength, B, is equal to, let me get a practical magnetic field here. So we want to go with a B field of how many Tesla? Making this up, so sorry. But I wanted to be realistic, so bear with me. Let's make B 18.0 times 10 to the, so millitesla. Milli is 10 to the negative 3. So 18.0 millitesla. Now you can look up the mass of proton and all that. You should be able to do. So let's say it's, oh, I made it, sorry. So let's stick with this problem. So let's keep it, make it an electron. Electron. So basically, I'm just describing this problem here. So it enters in, and let's see that it was moving at a speed that was let's say let's say 1/8 the speed of light. So let's say that the particle moves the electron travels with speed V is equal to 1/8 c. What I want you to do is use Newton's second law. And so we know that when we cut the field on, it's going to start to spin in a circle like this, based on everything we've discussed. Use Newton's second law and the information given to determine the radius of curvature of that circle. Derive the analytical solution first, and then put in the numbers and get the answer. So use Newton's second law to determine so let me read that back, make sure that makes sense. Assume an electron enters a region in which B is 18 millitesla. The electron travels with speed v equals 1/8 speed of light, 1/8 c. Use Newton's second law to determine the radius of curvature of the motion. So obviously, we know that when it does that, I turn on the field, it's going to start to spin in this cycle. This is a classic physics problem. It's called a cyclotron motion. Cyclotron motion. It's actually used in something called spectroscopy, where people are trying to determine the mass of particle. In this case, I'm asking you I'm giving you the mass because I give you the electron, and you should know the mass of the electron. But oftentimes we don't know the mass, and we can measure the radius experimentally because you can see it. Basically, you have a laser and you shine a laser, because the laser is just charged particles moving, and you shine them into a magnetic field, and you can start to see these spinning motions. You can see it with a microscope or a camera or electron mic, whatever and you could actually measure the radii of the cyclotrons that occur, and you can work backwards to get the mass of the particle. So that process of doing that is called spectroscopy. It's a certain kind of spectroscopy. There are different kinds, but yeah, it's a very standard thing that we do in physics all the time. People do it. It's basically a standard measurement. That is one of the ways that you can classify radiation, actually. So yeah. So see if you can set that up. So I've got you going. So what you're going to have to do is basically plug equation 1 into equation 3. But you could also have to put in basically, the magnetic force. And we know that we can use this definition, the magnitude of the force, to figure that out. To figure out what FB is, the magnitude is. And yeah, and then you can work to figure out what R is. So work on that for a few minutes as we go into.
Professor?
Yes.
C is the speed of light, right?
C is the speed of light. That's right.
Okay.
So C is the symbol that we use for the speed of light. Everybody knows what the speed of light is, right? Monica, what's the speed of light? Do you know?
8 times 10 to the 8, or 3
You're
times
right.
8.
You're right the first time. Yes, 3 times 10 to the 8th meters per second. That's right. And you can look these things up in the book somewhere, back in the book. They should have like the mass of it. I gave it to you, but you should have it should be all that mass of an electron and speed of light. Yes. So just work on that for a minute. Okay, how are we coming with this? David, the Wabo, how's it going? Angel? You making progress with this? Okay. Can you tell me what equation 4 looks like? Just in this process here, in this derivation. So let's go ahead and derive the analytical formula. So if I try to do that, Angel, what would be the next step? What did you do? Oh, I forgot you don't have a mic. So it might be a little bit difficult for you to, but go ahead and give it a shot. Maybe you can write it in. I don't know. Give you an opportunity to respond. Okay, well, neither. Okay, I mean, that would give you the acceleration, but that solves for the acceleration. But we're trying to find the radius, so you still got a little bit of work there to do. I had given you a hint to substitute in equation 1 into equation 3 and also the force. So that's kind of the route that's the route we need to go, right? We're trying to find the radius of curvature and it's not anywhere in this. So you have to kind of figure out where. You can see that there's radius here. So that's the start. You want to get that up there. But let's go with someone else. I don't know, Lucy, how's it going? How far did you get in the derivation? Okay, well, that's a start. Okay, Jason, you want to help us out? So, did you get far? Have you finished, or did you?
Yeah, I subbed the equation for AC, so I got FB equals mv squared over r.
Okay, keep going. Then what?
Then I subbed the force, the equation for the force, so Q
Yeah,
times
yeah.
V cross B.
Let's be cross B. Okay. Keep going.
Then I solve for R.
Yeah. So that's basic. So what did you do with? How did you handle this cross product? Tell me. Gotta evaluate.
Well, they're 90 degrees, so I can rewrite it as Q VB sine theta, but theta is 90 degrees, so that just becomes 1.
Right. Keep going.
So multiply R to the other side, and then divide by QVB.
That's right. So multiply through R. I've got R times Q V B equals M V squared. Now divide by QVB. And I have R equals M V squared divided by Q V B. And one of the V's cancels. So that goes. I've got one left. Now Q, that's actually the charge of a proton, which is the elemental unit of charge. So I'm going to go ahead and put that in. And so I have that R, the radius, equals M times V divided by E, the elemental unit, times B. And everything is known. I have the mass of an electron, I know that. All right, ME is equal to, what is it, 9.11 times 10 to the negative 31 kilograms. The elemental unit of charge is oh my gosh, embarrassing. 1 point times 10 to the negative 19 coulombs. What is it? 1 point what? Somebody help me.
6.
6.
1.6, thank you. 1.6 times 10 to the negative 19. And yeah, and C is equal to 3 times 10 to the 8th meters per second. And B is that thing I told you. So yeah, so this is called the cyclotron. Sometimes you see it RC for cyclotron radius, but it's a classic physics problem, and it's one thing we can work out very pretty straightforward with this. And sometimes you might be given the radius, and maybe you don't know what the particle is. Any of these things you can solve for. So, and this is the setup. Like you just have to evaluate the knowns and unknowns, and then you solve for the thing that you don't know. Okay. So when you put all these values in for this particular problem, you're going to have R is equal to 9.11 times 10 to the negative 31. And V is equal to 1/8 C, so that's going to be 3 times 10 to the 8th meters per second. And then I just put in the denominator. So the times 1/8, so I have 8 down here. And then 1.60 times 10 to the negative 19 coulombs. And then 18 times 10 to the negative 3 Tesla. And if I have all that in those MKS units, then the radius should come out to be meters. You can do might not be, might be worth it to do unit analysis just to convince yourself, but I'm not going to do that right now in the interest of time. And we get, did anyone do the math? What did we get? Result.
0.0118.
So the radius is 10118. What?
No, it's 0.0118
Oh, 0.01. Oh, sorry. 0.0118
meters.
meters. So let's say we could do that as
1.18 centimeters.
yeah, or maybe millimeters. Yeah, 1.18 centimeters, or yeah, probably, sure. Yeah, sure. 1.18 centimeters. Wonderful. So that's a pretty reasonable problem. Yeah, like that. The numbers that I chose for that. Cool. Yeah, so that's an application, cyclotron resonance. So that's why I didn't start the, I didn't want to cyclotron problem. I didn't name it that because I wanted to kind of build to it organically. But yeah, that's an application of the force on a moving charge. One application.
Professor.
Yes.
So it doesn't matter whether it's a proton or an electron, the elemental unit of charge will have the same, will remain positive.
Yes, that's correct. A proton and an electron have the same charge. That's right. I always sound like Darth Vader on your thing. Do you know what that is? Can everyone else hear that, or is it just ringing in my speakers?
I did hear it too.
Yeah, cool. Some sort of feedback is probably that happens with they call it an impedance mismatch. That's something we'll talk about. We should, yeah, we gotta get to it for RLC circuits. All right, yeah, so let's keep it moving along. Let me do another application. Gotta keep this rolling. There is something called the Lorentz force. Lorentz force. The Lorentz force is a combination of when you have an electric field and a magnetic field in the same region, they can both apply a force to a charged particle. Lorentz force. Now your book might not call it this. Some books do, some books don't, but it is. It's actually, you have Halliday and Resig. I think Halliday and Resig actually does say it. Lorentz force. Yeah, they do. Well, no, actually, they do that for some. Lorentz did a lot of things, so they have him in here, but not for that. Lorentz factor, Lorentz transformation. That's no, but it's the same guy, so they don't call it that. But Lorentz force is basically a combination of an electric force and a magnetic force. Lorentz force is I don't know, FL. I don't know if there's a symbol for it, but it's basically FB plus FE. So it's going to be equal to, on the charge, Q V cross B plus Q times E. Direct force. And that's just it. That's the definition. Now, it can be quite interesting when you take a look at environments where there's both an electric field and a magnetic field. I'm going to set this problem up. It'll be a working break, and then we'll take a 15-minute break, and you can kind of work on the problem at your leisure. But we talked a lot about capacitor plates and things a while back. Let's go back and pull up a capacitor plate. And let's put both and put an electric field inside that capacitor plate as well. That is, say we've got a capacitor plate, positive, the charge, positive plate is up here, the negative plate is down here. Now, what happens when I send a, let's say a positive charge, let's say a proton. Let's say I send a proton through this thing at speed v. Well, what type of motion? We've already done this problem. What type of motion will occur? Jason, what type of motion?
Parabolic.
Yeah, parabolic motion, right? If there's no field on, it just goes straight through. But if we draw a field is pointing down, it's going to be parabolic. So the particle will do something like this. It's going to curve. And this is the motion I was talking about, constant motion in the horizontal direction, accelerated motion down. There, you get a curved path, right? But there is something called a velocity selector, a device. Such that if I orient a magnetic field in this region in the right way, I can counteract the electric force. Now, by implication, Jason also is implying that the electric force on this thing is straight down, right? If I did a force, I'll put this particle in the center here somewhere, we know that there's going to be an electric force, Fe, which is equal to Q times E, that is straight down, right? At some point. Let me just, yeah, whatever. It's, you know, as this thing, you know, it would go straight through if there were no field, right? That's the horizontal line. Let's just say that it's on. And as we said, the parabolic path is going to deviate from that. Right? But at any point, if I were to cut the field on, there's going to be electric force. Now, first of all, let me ask someone this: what orientation would I have to put in a magnetic field such that the magnetic field on the particle is straight up? What would have to be the direction of the field for a positive charge? Got to work backwards on this. So usually I give you a field like we just did, and I ask you the direction of the force. Here, I'm giving you, I'm telling you that I want to have a magnetic force that's straight up. So what would have to be the orientation of the magnetic field on a positive charge in order for that to be the case? Let's go with Monica. I'll let you try it. Or no, David Edwards, are you there? You weren't there earlier, that's what I didn't call. David, are you there? Okay, AJ, what you go with? I'll come back to you, Monica. AJ, I know you're there. What's the direction of the magnetic field such that to get a magnetic force that's straight up?
For the magnetic field to go straight up.
For the magnetic force to go straight up, what would have to be the orientation of the magnetic field?
Negative?
I don't know what that means. You haven't defined what a negative direction is. Just tell me up, down, left, or right.
Oh, out of the board?
Well, let's try it. Run, wrap, point. Straight down. No. Try it again.
All right, so
Did you use your left hand to do that? If you use your left arm,
I
Yeah.
did. I did.
All right. So that, yeah. So the
Yeah.
try. So then
Into the
so
board.
now
Into the.
into the board. Yeah. All right. So that's also the thing I warned you about. Don't use your left hand. It's the right hand rule, not the left hand rule. Run, wrap. So wrap, it has to point in, point. Good. So if I make a magnetic field that is into the board, inside the region of this space, then presumably I could choose a magnetic a magnetic field that gives a force that is equal but opposite to the electric force. That is, if I can tune my magnetic field to the right field strength, then the magnetic force is going to be such that it equals the electric force. In such case, my particle would move straight through without deviating. Because we know if I cut the electric field off and I have the magnetic field off, we just did that problem. It's going to, go in a circle. I guess it would, it would go in a certain, centripetal motion. But if I cut on the electric field, now it's going to kind of make it bend. Maybe you could make it bend in all different orientations based on the strength of the electric field and the magnetic field. You can just switch them back and forth. Maybe the particle does that, and maybe it does this. But you can also tune them both to a certain place where the forces are equal and the particle goes straight through. Effectively, what that would be is if you consider the Lorentz force, it would be where the Lorentz force is zero. Because the Lorentz force is the combination of the electric and the magnetic. So what I want you to do is for let's see how, yeah, let's do this. How would I set the problem up? Let's say that we have I'm going to piggyback on this last problem. Um, well, no, let's just do it this way. Let's say that I have an electric field, a magnetic field of 18 millitesla, like we just said, and I have an electric field that is Sorry for the delay. I was just trying to find. Cool. Let's do this. Let's say that E is equal to 4,000 newtons per coulomb, and say 4,000, and B equals, let's go with the 18 millitesla. Determine the speed that this particle would have to go through without being deflected. What speed v of a proton would pass through with no deflection? So this is why it's called a velocity selector, because say you set a bunch of particles in, various particle beams or a beam with several velocities. Maybe it's a wide beam, so it's not like a laser. It's just, you know, more like a, I forget what you call those things, phosphorus plate, photo gun or something. So it just kind of spews out particles and they have various velocities. Only certain velocities would make it through, right? You could set it so that many of them are deflected on the parabolic path and they hit plates, but some of them actually get all the way through without being deflected. So based on the setting of E and B, that's only going to allow certain particles to get straight through. And you know, you might have some kind of that'll deflect at certain places, but you know where you sent the beam in, and you can have a you know, like what position, vertical position relative to the device. And you can have a sensor over here that's at that same vertical position relative to some reference point. And only the particles that hit that detector are the ones that actually get all the way through without being deflected, even though some could be deflected and still get out of the device. So if for a velocity selector, E is 4,000 newtons per coulomb and B is 18 millitesla, at what speed V of a proton would pass through the device with no deflection? So the way you could apply that several ways. You could just apply Newton's second law, but I've already set it up for you. Well, actually, it's Newton's first law, right? Because if it's not deflected, then the total net force on the object is zero, and that's Newton's first law, right? That net F equals zero. But since I defined this Lorentz force for you, you know that net F is the Lorentz force, which is the combination of both of these forces. Yeah, but be careful because this plus sign is kind of an inherent plus sign because I've used vector notation here. But when actually you take the magnitudes of those forces, you have to consider the relative directions. So the electric force is going to be down, the magnetic force is going to be up, as we said. Yeah, so let's see how fast. Now, I hope I didn't screw up because I might have chosen numbers such that the speed is faster than the speed of light. I hope I didn't do that. I tried not to do that. That's why I was waiting. I don't want to make an unrealistic problem because that is conceivable. But I think maybe this is going to be okay. These are going to be reasonable numbers. Might not be though. I might have screwed up. But if I did, let's just bear with me on that. I have to change it once we, but go ahead and get whatever the value is. Go ahead and get that, and then we'll see. Actually, you know what? I did. Let's change the magnetic field. Let's change it to let's make it a very high magnetic field. So make it something like B is equal to 18 times 10 to the 5th Tesla. Yeah, I can see it already. That 18 millitesla would have been unrealistic. The particle would have to go faster. So I think this is going to be okay. So go with that. Go with that. That's going to give a relatively reasonable speed. Okay. Actually, it doesn't have to be that high. Just make it 18 Tesla. So as opposed to 18 milli, just make it 18 Tesla. That might make it too small. So 18.0 Tesla, which is actually a very high field. Relative, high enough. Anyway, so 4,000 Newton Coulomb and 18 Tesla. Let's take a break, and let's take about 10, 15 minutes, and we'll come back and look at it. Probably now do another application as well called the Hall effect. So we good? Any questions? All right. Let's take a look at this guy. Yeah, so this is set up such that we said that we want to know what is the speed of the particle such that it's not deflected as it moves through, given these two fields. So if you have a particle, let's just do a kind of a free body diagram. As it moves through, we're saying that there's two forces on it. One is going to be Fe, which is down, and the other, which is Fe, which is up. Okay. They're equal and opposite, so the acceleration is 0, so the particle passes through with no deflection. Well, that's, you could start from the first law, as I said here. I'll just keep going here. So the net force on the particle is 0. Well, what is the net force? Well, it's the Lorentz force. Now, when I drop the, so I guess FL then equals 0. Well, that's going to be FB vector plus Fe vector equals 0. But now when I drop the vector notation, I have to put in the relative directions. That's called up positive and down negative. So that will be FB minus Fe equals 0. Now we put in the magnitudes of those forces. The magnitude of FB is going to be, what do you say, a proton? Yeah, whatever. Let's just do Q for now. So Q, V, B, sine of theta, but theta is 90 degrees. That's the direction between B and V. 90 minus the electrostatic force, which is QE. So Q times E equals 0. Well, you can see Q is going to cancel out. Well, both sides, each one. And the only in sine of 90 is 1. So when I solve for V, I get that the speed is equal to E. So I take E over as plus, then divide by B, so E over B. And that's a classic result. It shows you that the unit associated with the ratio of E and B is the unit of velocity. And that will give us, the speed that it would need in order to not be deflected. Or actually, it's really the other way around, right? It's not that we actually control in E and B. So really, I guess what you would say is that those are the values of the fields such that it would allow that speed to go through, that particular speed. So if you put it in, you're going to get 4,000 basically divided by 18. So that's how I could see whether or not it was going to be realistic or not. And so we're going to get, did anyone get a value? Calculate it. It's approximately,
I think it's 222.22.
222 repeating meters per second.
Yeah.
Okay, cool. So I guess we should, significant digits, I only had 2 significant digits really, so let's just be careful on that. So approximately 220 meters per second, right? If you round it off.
Professor, can you repeat why is it FB minus FE?
Yeah, because there's different directions here, right? Like you have to take it into consider, you know, whenever you have vector signs on there, it's saying that you're just doing it's superposition, but you have to add them according to their relative direction. So when I drop the vector symbol, then I have to put in the relative directions. It's just notation. If I hadn't started with defining the Lorentz force, you would have even questioned it, right? You would have basically maybe started going from here to here. But whenever you're adding vectors, technically you know, if you have the vector notation, then you don't usually put in a sign. The sign happens after you start to define the relative directions.
Yeah, so that means that sometimes it's gonna be plus and sometimes it's gonna be minus, right?
Yeah, and this problem, the forces are in 2 different directions. One is up and one is down. So how do we represent that normally?
What do you mean?
You're asking me.
Yeah, I get why it's negative. Now that I hadn't seen the arrows, were the direction of the forces, but I mean, I get that, but my question now is sometimes depending on where the forces are, their directions, sometimes it's gonna be positive, sometimes negative. Because you said that if you hadn't defined the Lorentz force how you did at the beginning, we could have gone straight to the FB minus FE. So I got on that.
You're still confused?
I mean, when you said so is it always gonna be FB minus FE even after we do the direction analysis for the vectors, or can sometimes be FB plus FE?
It's not always going to be that. It's whatever the relative directions are. In this particular problem, the forces are opposite.
Oh.
So that's what I meant. In this problem, I could have gone directly from step 1 to step 4, given what the directions of the forces are in the problem that I set up. But in general, you just would, you would put in whatever, you would just evaluate the directions of the forces as you need to. In other words, this is kind of a special example. Like, what if you have the forces something like this, like maybe FB is here and FE is like that. Well, now you have to add them vectorially. You have to find the components and things, because it's not the angle here. The angle is 109 degrees, so they're along the same coordinate direction, just opposite. So you can add them directly. Here you can't add them directly because they're not pointing along the same direction. So what do? You do vector analysis. You follow me?
Yeah.
Yeah. So I guess the short answer is in general, no, it's not going to be just FB minus FE. It's going to, you have to evaluate the relative directions of the forces according to the physical phenomenon that you're investigating. But whether that's true or not, this still is an appropriate equation. That's why I wrote it that way, because it just implies superposition when you write it with a vector symbol. You know what I mean?
Yeah.
You sure?
Yeah, I just wanted to make sure.
Okay. All right. All right. One other issue, I forgot to say something on that. I guess I said it, but I didn't go one. I just noticed in your book on the last problem with the cyclotron problem, we could go one step further and define the frequency, the angular frequency of the rotation. So let's just step back for a minute and go back to that. Right, we had gotten that what was it? Well, R was equal to M times V divided by Q over V. We could solve for V, right? V is equal to R Q V over M. But from rotational motion, we know that we can define an angular speed or an angular frequency. It just depends on how you want to think about it. Omega is equal to V is equal to, oh my gosh, I can't believe I'm forgetting. Omega times R, right? Yeah, this is the relationship of linear speed to angular speed. So omega is equal to V divided by R. Well, if I stick, we know that it's spinning. If I stick this V and put it into here, then that gives me I think I did say cyclotron frequency or cyclotron resonance is what I called it. But this is you can think of this angular speed of the particle as an angular frequency. So if I put that in, that's going to be M or R Q V M over R. The R is canceled. And the angular speed or angular frequency of the particle that's spinning around in that magnetic field is equal to Q V over M. So that's called the cyclotron frequency. So cyclotron radius, the speed of the particle in terms of B, and the cyclotron frequency for a particle spinning in a magnetic field. let's do the Hall effect. Hall, Hall field, Hall effect. It's related to all of these. It's another application. Oh, wow. Okay, let me do that as well. Yeah, I'm just looking at your book. They kind of, yeah, beat this to death, which is not a bad thing. Before I do that, let me just, we can also do the frequency and the period. So this is angular frequency, but then I'm just, because your book has it, you know that omega is equal to 2 pi times f, the regular frequency, where f is just cycles per second. This is radians per second, but this is, omega is radians per second, but f is cycles per second, it's numbers per second. So, and this is the relationship. All these are mechanics things that you should have defined those in mechanics when you did oscillations. So I'm not going to review where that comes from, but it's just definitions. But once you have, once you get the velocity and the radius, you can just find all these other little things. So they do that for this cyclotron resonance problem. So now I can take omega and plug it in here, and that's going to give, or solve this for f, and that's going to give me omega. So I would give me f. So f is equal to 2 pi divided by omega. So that's going to be equal to 2 pi. 2 pi, I guess when you flip it around, it's going to be m over q times b. So that gives you the frequency for a cyclotron resonance. So you have the angular frequency, the velocity, the radius. And finally, you can do the period, the period of motion of the thing, because you know the relationship between frequency and period. So the period for cyclotron resonance then is going to be 1 over the frequency. And so therefore, the cyclotron period is going to be QB over 2 pi times the mass. Did I do that right? Somehow I've screwed up. I've got it flipped around. Why? Isn't omega equal to 2 pi f? So if omega is equal to 2 pi, keep it on the bottom, right? R is equal to mv over qb. V is QBR over M. Omega is QB over M. Oh, wow. Can't do algebra. Sorry, folks. It's here. I flipped this around. So solving for F is omega divided by 2 pi. Sorry. F is equal to omega divided by 2 pi. So that all this flips around. It's QB over 2 pi M. And so then this is going to be flipped. It's going to be 2 pi M over QB. Okay, there you go. Yeah. All right. So that should complete everything about cyclotron resonance. Yeah. It has several applications, actually. Even in regard to the magnetic field of the Earth and the solar wind, like the aurora borealis. See those beautiful colors. When those charged particles coming from the sun hit the North Pole, the aurora borealis is an application of this. What happens is that the magnetic field of the Earth is very strong up there. And essentially what happens is the particles accelerate. But how do they accelerate? Like this. If you could actually see them, you would see them spinning around, as they're interacting with the poles. Now, there is an interesting side effect that whenever a charged particle accelerates, whether it be in an atom, jumping from level to level or wherever, it emits a photon. And the photon is associated with the frequency of the energy that's causing it to accelerate. So, like in a particle, in an atom, when that happens, the energy of the photon is going to be associated with the energy level from that it jumps to or from. And so the photon is going to come off with that same energy, but usually the energy is such that it corresponds to an electromagnetic wave in the visible spectrum. And so it glows. It glows with certain colors associated with the frequency. And that's what phosphorescence is. And so we see it. And so that's why the colors, and so the same thing happens in the aurora borealis, like when those things start to spin and accelerate, they pop off photons, and the photons have an energy level that is within the visible spectrum of our eyes. And so we see it, but it's also why the colors look kind of like phosphorescent, because it's the same electromagnetic wave or range of frequencies that corresponds to phosphorescence, what we normally call phosphorescence, like glowing toys and things like that. In the case of the toys, the reason that you get the acceleration is because incident white light hits the atoms of the thing, and the atoms absorb the energy, and so electrons in certain energy levels get too much energy for the levels where they're of the energy levels that they're in, and they jump to a higher energy level. And when they do that, they emit a photon that your eye sees as a certain color, purple or green or whatever. And then after a while, it loses that energy and drops back down to the same energy, the original energy level, and then it still emits the same photon of the same frequency. So the aurora borealis is kind of a side effect, a secondary effect of the cyclotron process. That it accelerates because of what we said. And it's a different kind of acceleration, right? It's not like jumping energy levels necessarily. Could be, but if it's some larger atom or something that's accelerating. But I think you can also just have just charged particles that are separated from atoms, and they start to accelerate, but they also send off different process than jumping energy levels in an atom. But still, you get energy that emits radiation that is sensitive to our eyes. So it looks like the phosphorescent colors of what we would normally call phosphorescence. So it's a whole wide range of applications of cyclotron resonance, not just in the spectroscopy that I talked about, but it's all over the place. Yeah. All right, so we got phosphor, we have a cyclotron resonance. Any questions about that? Hall effect, another really interesting and kind of easy thing we can solve based on this physics of magnetism. It was discovered by some physicist named Hall. I don't know, I think he was British. But let's look, let's take a look. Oh God. Oof. Let's take a piece of metal, a flat piece of metal, like this aluminum. This is aluminum. This is actually really good. Now this is cylindrical, but you know this part is flat. Let's say if I could just have a flat slab of aluminum. Oh, excuse me. This eraser board here, eraser panel. I could pull that off. It would just be a, you know, a slab of maybe it's a couple millimeters thick and 2 inches. So just visualize a slab of aluminum that, you know, is just rectangular in shape. And we know the Einstein model. I've discussed that at length, I think. Oh, yeah, of course. And so visualize the Einstein model of a conductor. And what do we have, right? We have the atomic sites. We've got the electrons around those guys. We've got the free Fermi electrons, the sea of electrons in there. And they're all vibrating, but no, it's random motion, right? No collective charge or currents or, you know, accumulation of charge in a particular place. Now, that's a pretty complex model to look at. So, but that, I want to evoke that because that is what we're talking about here when we look inside this metal. But we know that the atoms don't move that much. They vibrate, but they're not going to translate. The bound electrons around the atoms don't really move. You know, they can do the thing that I said. They can jump back and forth between energy levels for whatever reason. But really, it's the free electrons, the Fermi electrons, the sea of electrons that are used, that are given up by each shell of the atoms, and they're used collectively. So kind of let's just focus on that for now. Let's just say that there's a whole bunch of electrons in this thing, and they can move. In fact, I think what I should do is redraw this so that the material looks more like, I'm going to set it up like this. So I've just changed the orientation of the material. So we got free electrons in this thing, and it's a metal. So if we apply a voltage to it, we can cause current in the object. So let me attach this thing to a battery. I'm going to have a battery right here, and I'm going to connect. And let's do the INF. Let's just INF associated with the battery. It's positively, negatively. I'm going to connect that battery to my piece of metal so that I can cause current to flow through my metal. All right. So if I set up, so when I close the switch, I'm going to cause current to flow in this circuit in the clockwise direction. So current is flowing through this piece of metal from left to right. Now, I'm going to place this magnetic field. I'm going to place all of this in a magnetic field that is perpendicular to the board. Now, again, visualize what is happening with that current. Well, we talked about current a couple of different ways. We talked about it in terms of the definition of current. All right, so current is equal to, is defined as, you know, Q over delta T, or dQ dt for, you know, instantaneous current. But we also talked about current in terms of the microscopic view, that is equal to the charge times the charge density N times the drift velocity V sub D times the area. And this is the thing that I'm really that's the version that I'm really concerned about for this problem, that macroscopically, once we apply a voltage to this wire, we created a potential hill in these free electrons that were in my metal, whereas they were once had random motion. Well, they still have that random motion. I think I told you that, but now they're going to start to drift in a particular direction, namely the direction of the current. And that's what current really, you can think of current from that model in that way. So they're drifting down and they basically have a velocity, is what I'm saying. That we can think of the charged particles and again, remember what I'm gonna, it's gonna be holes, right? So when I draw a positive charge here, don't be fooled. That's not an atom. That's not a proton. That's a hole. That's the absence of an electron, okay? But I'm gonna deal with holes because I like doing that. It's easier for me to do positive, so it's negative in my mind. Anyway, drift velocity. And so we have a V sub D, a drift velocity of the free charge in that metal drifting from left to right. Everybody good so far? Lucy, you understand what I'm saying? Any questions? Okay, good. Thank you, Angel. Now, Angel, go with you. So, Angel, so you get another chance. I asked you earlier, but here's another. I'm now going to superimpose an external magnetic field on this whole space in which the circuit exists. Watch. I'm going to make it, I can make it any direction I want. We'll make it perpendicular for ease, but let's say that I place it out of the board. Yeah. So there's going to be a magnetic field that I'm going to cut on, and it's every place, you know, in where this thing is. I'm going to put it over it because I don't want to get it messy, but you know, the magnetic field is, you know, out of the board. And so it's cutting through this, you know, wire. It's in the vicinity, the wire, my piece of metal is immersed inside the field. So Angel, first of all, when I cut that field on, will these free charges inside my metal that are drifting with a drift velocity V sub D in the direction of the current, will they experience a magnetic force? Yes or no? Angel? I have all the ingredients. Magnetic force is, a magnetic force is defined as a charge with a velocity in a magnetic field. So if a charge has a velocity in a magnetic field, there will be a magnetic force, and that will be equal to the charge times the cross product of the velocity of the charge times the cross into the magnitude of the external field. Here I have all the ingredients. I have a charge, certainly has a charge on it. It has a velocity, and now it's in the vicinity of an external magnetic field. So I ask you again, will those holes, H-O-L-E-S, experience a magnetic force in that thing? Angel. Yes, they will. Oh, Lucy, did you also answer? I didn't see you up there. Did you answer yes as well? Or was that for something else? Was that for this? 1047. Yeah, it must have been. So sorry, I didn't see you. But yes, Lucy, you were right. And Angel, you are now also right. Okay, good. Very good, Lucy. Now, Angel, there is a magnetic force. What is the direction of the magnetic force of the charged particles inside my piece of metal? I was confused with the metal part of the equation. Wasn't sure if it had any bearing on the equation. Yeah. I mean, I'm just making a piece of metal, I'm making it big because it's easier to see. But the same thing would actually happen even if I just use a little piece of wire. But it's just hard to kind of visualize in my opinion. But here we got a big flat piece of metal, so it's easier to think about the charge inside of it. That's why I'm using it. So yeah, so it doesn't that, and I get what you're saying, right? Like all these things before, the charge was independent of any particular physical thing. Like I placed one charge inside a capacitor plate. But that's not realistic. Like, you don't think it's not gonna be just a charge for, I guess there is, but those are more kind of idealistic setups just so we can understand. When you actually start to think of these things practical, in practical applications, then yeah, it's a little bit more complicated than just the kind of basic scenarios that I set up. So where we would see charge is inside a metal. So it would be the metal inside a capacitor plate or the metal inside of a magnetic field. Or like in case of the aurora borealis, like that's a cyclotron, but there's a whole bunch of other stuff going on. The fields are not constant. They're going into the earth. So this is a little bit more complex in that way that it's starting to get a bit more realistic. But that said, we still have free charge inside a metal. They're free. They can do what they want, under certain restrictions. And the external the magnetic field, as you know, cuts through anything. Right? Magnetic field is still going to cut through the metal, even though the metal is there, and the charge will still respond, to that. But good point that you made. Yeah. So, can you tell me, Angel, what is the direction of the magnetic force on holes moving to the right? Do the right hand rule. Here's your second chance at it. Run rat point. You say down. Very good. Awesome. Run orient my hand so I'm running parallel to V, orient my hand and wrap my finger so that it's parallel to B out of the board. Point down, positive charge, stay down. Awesome. Very good. Very good. Now, that's just one chart I've drawn just for the purpose of illustration. But copper, for example, has 10 to the 23rd, I think, either 22nd or 23rd charges per unit volume. 10 to the 23rd, right? That's 10 times, and 1 times 10 to the 23rd. So there's a whole lot of charged particles in most metals. And so it's not just one charge that's going to be forced down, it's quite a few. But they're in a piece of metal, so they can only go so far. How far do they go? Well, they go all the way down and they start to collect on the bottom of the piece of metal, right? Like when it's like we said that, if it were a large piece, whatever, I mean, if it were just free, it would go in a circle, but it can't, right? It is kind of, pushed down. And so it would kind of do something like this. But at some point, it can't get all the way around. So it just stops there. So you're going to have positive particles start to accumulate all along the bottom of the metal because they get stuck there and they can't move. So they're deflected down. Well, remember, that's the absence of a positive charge. Sorry, the absence of a negative charge.
what's actually happening to create current is we actually have negative charges that are moving in the opposite direction. So let's go ahead and, I never really considered that, but let's go ahead and consider that for right now. Let's say that the actual, because the only thing that moves in metal are electrons, right? So there's an electron here, but the equivalent current, I, is going to be the electron moving in the opposite direction. So now be careful, we don't have to flip because it's an electron now. But someone do that one. Who hasn't answered today? I called a couple of people that have an answer. David, you want to give this a shot? David Edwards, are you there? David Edwards? No? Okay, Edmund. Calling you earlier, you weren't there. Edmund. All right. Well, Lucy, I think you had asked, let me give you a shot because you had answered earlier. So you want to do, if you have a negative charge, what would be the direction of, well, first of all, it's moving, so it's going to have a magnetic force. Oh, wonderful. Lucy says up, and you'll be right. Very good. Using the right hand, run, wrap, point. It's up. So what we're going to have is negative charges accumulate on the top. Okay. Now, initially, before I turned on my magnetic field, as we know, as we've been doing problems, weeks before and everything, current was just going to go through it undisturbed, no problem. But when I turn on that magnetic field, now there starts to be an accumulation of charge on the top and bottom. And what does that look like? You have positive charge accumulating on the bottom of the thing, negative charge up there. Well, it looks kind of like a capacitor. You're going to start to have an electric field that is perpendicular to the direction of the current and perpendicular to the direction of the external magnetic field. And that thing is going to be pointing up. Like that. That electric field is called a Hall field from the physicist who first discovered it, E. Hall. In fact, you can't really measure field. What you measure is voltage. But what you're going to find is there's going to be a voltage at the bottom plate and literally a voltage at the top plate. And that voltage, obviously, that delta V is called the Hall voltage. There's a relationship between the field and the voltage, and this is a constant field, it would be constant. And we know that if the metal, the geometry of the metal, let's say that its length is L, has length L and width D. And width D here. Well, the electric field there, the relationship between the Hall field and the Hall voltage is that the Hall voltage is going to be equal to, I'm just going to call it, it's going to be equal to the Hall field times D, the width of the thing. Okay. All right. Well, cool. We could actually derive what these things are. So that's the relationship we have based on our discussion from last week. But we can derive these things. We can talk about what they are in terms of current, in terms of magnetic field B, external field B, and things. So let's do that. Let's see. Let me set up something for you. See if I can. So this is B. Hall voltage, yeah. So Well, I guess we're going to need a resistor in the thing. So let's say that we have a resistor in this deal. Put a resistor on the wire, R. We have a battery voltage there. Let me set this up. I'm going to make it straightforward. Actually, I don't have this written in my notes. I'm doing it kind of top of my head. Sorry. Oh, ouch. That's why I'm kind of hesitating here. I don't think I did that before like this. Let me screw it. Yeah. Voltage. Yeah, let's just do, oh, here. Yeah, they could kind of charge this, all that. I'm gonna make it simpler than that. Straightforward. Yeah, so let's do it like this. Let's say that yeah, I guess we can, what we're gonna see is it's something similar to like the Lorentz force I did a while back, where as that Hall field builds up, you can see that its direction is gonna be, so there's gonna be an electric force on the particles, right? The field, the field should point from, field points from positive to negative. So for a positive charge going through, where the magnetic force is down, as this field starts to build up, the positive charge begins to feel an electric force that's up, right? Because it tends to want to be attracted to the negative charges. So at some point, the Hall field will reach a maximum value. And that maximum value is going to be when the Hall force on a charged particle is equal and opposite, or the electric force due to the Hall field is equal and opposite to the magnetic force. And at that point, when the Hall field reaches that point, then the current will start to pass through without being deflected. Does that make sense? So initially you have current going through, right? I turn on the magnetic field, what you would see is the current would go to zero because no current can get through because it's all being deflected, all the charge. But at some point, gradually the current will start to increase again. Why? Because as that charge builds up on the plates, an electric force builds up, which is counteracting the magnetic force. And at some point, when the force, so if I did a free body diagram of the charge, of a positive charge, right? Going through, initially it feels FB, force down. But as it accumulates, positive charge at the bottom. Now it's going to start to feel an Fe that grows until Fe is equal and opposite to Fb. When that happens, we're back to the net force on a positive charge being 0. And so therefore, the current would drop to 0, then build back up, and then gradually just go back to what its regular current was as it goes through with that Hall field in there. Yeah, so it's a little bit of a complex problem. So let me see what I would think about what I want you to calculate on this stuff. Because we could still do, you're still going to have like a velocity selector in a sense, but it's just in terms of current. Yeah, I don't know. People talk about current density and stuff like that. I don't know. I mean, what you could say is a couple of things we could just say here because we've already know it. This drift velocity here is actually the drift velocity of the current going through. So you could do stuff like, we could just write down results that the drift velocity associated with the current is going to be equal to the Hall field divided by the external magnetic field. We could just write that down. But because, we wouldn't necessarily know the Hall field, right? You have to measure it. I didn't get an equation for it yet. But we know that electric field is equal to voltage divided by distance, by the width. So you could say that the drift velocity is equal to a Hall voltage, delta V, which is the voltage. It's not associated with the battery, not necessarily, not directly, but it's the voltage across the width of the metal. So that's delta V Hall over D times the external field. Yeah. Yeah. Some people like to do this in terms of current density. I guess you could do that. I defined current density for you the other day. Okay, sure, maybe. Coming from this equation here, remember I defined current density. I said that current density J is equal to the current I divided by the area. That's just the definition. But if I use the macroscopic view of current and plug it into that equation, then the current density is equal to Q times N times V sub D. Okay. So I could now write current density in terms of my Hall field because I have a relationship for the drift velocity. So the current density is equal to, you could do the same thing with current. I just could have plugged this into here, but whatever. So current density then is going to be equal to the charge times number density times the Hall voltage divided by D times the external field. Or I could put it in as field, and I could just as easily say that that's also equal to Q times N times the Hall field over the external magnetic field is equal to current density. Or I could multiply through by A and just call it current, right? Current is also basically just stick either one of these equations in here. Anyway, I don't know. I think that's enough of that. So this is really what I want to kind of emphasize. It's similar to, so that's the Hall field.
Get some qualitative questions associated with that. Yeah. So anybody have any questions about Hall effect or Hall field or anything associated with that? We take a quick break. When we come back, I'm going to finish up by deriving the. So we've looked at the force on a current on a charge, but we can now look at the force on a current carrying wire. Get that done for you before we leave class. Be right back.
Okay, 10 minutes. All right. So yeah, that's a Hall effect. It's a thing, it's worth it's again one of these situations where there's a lot of practical applications associated with the Hall effect. It's really nice, and it's one of the ways that we characterize the electrical properties of materials. Basically, people, I don't know if you know, but like people are material science, as you may know, is a whole area of science, but and it's its own separate area, but I think that's a whole degree in itself. But physicists and engineers, also, there are areas of engineering and physics that are also material, study materials, and they work with material scientists. It's kind of related, but it's a big deal. It's a huge area of physics, everything from electronics to aerodynamics, uh, you know, uh, the materials that spacecraft, airplanes, things are made out of, all kinds of stuff is important. And when you make a new material, one of the things you need to do is to characterize it. And there are certain specific characterizations that are standard characterizations. Hall effect is one of those things. Cyclotron, like measuring the mass of material is one of those things. The mass of particles, or the mass of, uh, the cyclotron frequency under certain conditions. Because like it's things you don't really think about a lot of things, but like say the space shuttle, right? Say the space shuttle is going off someplace, or some enter some craft that's going to be traveling out in space. Well, now it's affected by, whereas normally airplanes and things are protected, like all of us are, by the atmosphere and the magnetic field of the Earth. Once you go outside of the Earth's protective environment, you're not protected anymore. So, you're exposed to external magnetic fields of things, external whatever, like solar wind and stuff like that. And so you want to know material science becomes important because you want to know how those materials, the walls of your craft, are holding up, how they're responding to external stimuli. So you don't want your craft to light up and be static, or whatever, static electricity, and and not understand that. So these kind of characterizations they're important for those kinds of, we start to characterize materials once you make them or fabricate them, so that you can, it's a way to understand how these materials will respond to external fields. So that's why these things are in the chapter here, why they're important. Oh, yeah. So I can finish up with a derivation that will get you to, we've talked at length. All of these things, these concepts we've discussed, have discussed the magnetic force on a single charge or collections of single charges. Well, we can also think about the collective force, because as Andres, was kind of alluding to, or Angel, I'm sorry, with his the comment that he made. Usually we don't think about charges free of being inside some kind of material. And if they are, then if there are charged forces, magnetic forces on for a wire, a current carrying wire, we know that there are going to be magnetic forces on the individual charges, but the individual charges are inside a wire. So because force abides by superposition, if you add up all the forces on the individual charges, you should detect a force on the wire itself. And so, so we can do that. And we can write, we can have a derive an equation for that. But this last derivation is basically just a culmination, kind of a extension of the force on a charge, but looking collectively at the forces on n number of charges within a wire. So this is the magnetic force on a current carrying wire. Yeah, so here we have a wire. Let's say it's looking at the cross section of a wire, and it could have been connected to a battery, like I had done here before, so that we have current flowing in the wire from left to right. And we have an object that is experiencing a drift velocity. So we'll go with a hole again. And the hole is drifting with V sub D through a cross-sectional area that is a cross-section of the wire. Remember, that's how we define current in the first place. That it's a number of charges that flow through a cross-section of the wire, where this is cross-section has area A. Okay. Now let's say that the wire has length L. So we know that the individual charge here has a force that's defined by the force we've just been talking about. So on one charge, on an individual charge, the force FB is, we'll just go with the magnitude. Well, it's QVB sine theta, we know that. And it's a simple derivation, right? First of all, the you know, the direction between V and B is 9 degrees in this particular case. Oh, sorry, I didn't put it in the field. So let's say put in the field. Put in an external field. This time I'll make it into the board. It doesn't really matter. So let's say that we have an external field. And the external field is there into the board. Right. So this is going to be, the thing is 90 degrees, so we get QVB as a result. But let's say that, you know, so we get a bunch of charges, and I'll do this quickly now. So we have N number of charges. And basically, we have individual force, this force on each of these charges. So the net charge is essentially the net force on the wire is going to be equal to the vector sum of the forces on all the individual charges. So essentially, what I'm going to have is the total force, F total, is going to be equal to N times the force on an individual charge, which is N times Q times V times B. But one thing we can do is to find, which we've already done, the number density. Number density is the total number of charges per unit volume. But volume is equal to area times length. So that N is equal to number density times area times length. So if I take, that equals N. So if I take N and substitute it into N here, then I have that my total force on the wire, so F on the wire is equal to N times A times L times Q times V sub D, yeah, V sub D times B. So let me group some stuff together. Let me group together, so L is going to be out, the B I'll put over here. So what's left is N Q V sub D times A. So I've just kind of regrouped. And what is that thing right there? Well, that's my current. That's my microscopic view of current. So I get LB times I, force on the wire. And I can rewrite that a different way. I can write it as well, what we normally do is I is a scalar quantity, but we can kind of make it, L is not, L is a vector quantity, and length can be a vector quantity. But what we normally do is kind of put the I and the L together, because we can do something like IL, and we put a vector on L cross B. And we can write this as a vector quantity, where the IL go together, and the I gives the direction of L. So in this case, I is going to the left. So if I were to do a cross product, I in the direction of L or L in the direction of I cross B gives a force on the wire that's up. But that would be the same force, the same direction, which it should be, of the force on any individual charge. Run, wrap, point, up. So the direction of, as I told you, the net force on the wire is really just a vector sum of all the forces on the individual charges. But if a positive charge has a force up, run rat point, then the wire itself should be up. So again, looking at it from the point of view of the wire, you take the direction of L, the length of the wire, from the direction of current through that wire. So L, B, cross B, up is going to be the direction of the force. So the current carrying wire will have a force ILB, and the magnitude of that force will be ILB times the sine of the angle between the direction of the length of the wire in the direction of current and the direction of the magnetic field. Okay, so that's it.